Hello and welcome to another calculus video. In this one we're going to do section 2-7 related rates, and we've got two bullet points: find a related rate and use these related rates to solve real-life type problems. So the book says you've seen how the chain rule can be used to find dy dx implicitly. Another important use of the chain rule is to find rates of change of two or more related variables that are changing with respect to time. For example, when water drains out of a conical tank, like we see over here on the right, the volume V, the radius R, and the height h of the water level in the tank are all functions of time. So here the water tank is full to the top. We've got the depth of the water, or the height of it in the tank, the radius from the center of the tank to the edge, and the volume would be the entire amount of water in the tank. Now we unplug the bottom and the water drains out. So everything is changing. As the water level drops, the height is dropping, and the radius is also shrinking, and overall the volume is getting smaller and smaller. So all three things are changing, and they're all changing related to time. So they're all related by time. And it says, knowing these variables are related by this equation, the volume of a right cylinder, conical cylinder like that, is a third pi times r squared h. We can derive both sides implicitly with respect to time and get a related rate equation. 1/3 pi r squared dh dt plus 2rh dr dt. From this equation, we can see the rate of the change of the volume V is related to the rates of both h and r. Remember this here, this dh dt, that is the change in the height as time goes by. Dr dt is the change in the radius as the time goes by. And that all leads us to the change in the volume as time goes by. So here in example one, it's not really an applied problem. They sort of just spoon feed everything right to us. The variables x and y are differentiable functions of t, and they are related by this equation. So we have y equals x squared plus 3. They want us to find dy dt when x is equal to 1, given that dx dt is equal to 2 at that same moment in time when x equals 1. So we got a dx dt, we've got a dy dt, we've got an x value, we've got an equation. So let's derive it. Derivative of y will be dy with respect to time dt equals, here we're going to derive x squared. That's going to be a 2x, and again we are deriving with respect to t, so we get a dx dt, and the 3 derives away. And let's go back, reread the problem again. They're asking us to find dy dt, and we've got dy dt by itself, so it looks like we're just going to plug some values in over here. We've got a 2, and then x, well, they tell us here x is 1, so we're putting in a 1 for x. And dx dt, well, they told us dx dt is equal to 2. So our dy dt is equal to 2 times 1 times 2, or 4. Okay, that was an easy one. They're going to get a little trickier. In that first example, we were given an equation that related the variables. We were asked to find the rate of change of y when x was equal to 1. So we're going to see this in the rest of the examples. I encourage you to do this in your homework. We've got an equation. In this case, it was y equals x squared plus 3. They gave us a rate, dx dt was 2, and they told us when to sort of stop time to analyze the problem, when x was equal to 1, and what they wanted us to find. So in each of the remaining examples, we're going to create a math model from a verbal description. It does help to stay organized by having an equation, given rate, and find, where you just fill in those blanks. Sometimes I do the equation last. It might be the hardest part to figure out. Example 2, ripples in a pond. A pebble is dropped into a calm pond, causing ripples to form in concentric circles as shown in the figure. So here the pebble goes plop in the middle, and the ripples head out from the center, creating those concentric circles. The radius r of the outermost ripple is increasing at a constant rate of 1 foot per second. When the radius is exactly 4 feet, at what rate is the total area A of the disturbed water changing? So I'm going to do given. That's supposed to be an E. Given, find and the equation that ties those variables together. There we go. So let's reread this. I'm going to get my highlighter out. Get this out of the way. Okay, the radius r is increasing at a constant rate of 1 foot per second. When the radius is 4, at what rate is total area changing? So always look for the word rate. It's kind of a given or a giveaway, because the given and the find stuff are usually some rates of change. So the radius is changing at a rate of 1 foot per second. Radius, rate, 1 foot per second. So our given will be dr dt. The rate of change of the radius, dr dt, is equal to 1 foot per second. Okay, when the radius is 4, at what rate, so here we're asking what rate, this is our find, we want to find what rate the area is changing. Well, the rate of the area will be dA dt. So dA dt equals question mark. And then usually with the find is we want to freeze time at some moment to analyze the problem. And here it says when the radius is 4, at what rate is the area changing? So we want to find dA dt when, where was that again? When r equals 4. Find dA dt when r is exactly equal to 4. Okay, so what ties all these together? We're talking about concentric circles, we've got area, we've got radius. Well, area equals pi r squared. The good old formula for the area of a circle. Right, I'm going to start a new slide here. I don't want to erase anything. Area equals pi r squared. We've got everything we need, the given rate, the what we need to find, and the equation, so let's derive. Derivative of area, dA, with respect to time, dt. dA dt. Now remember, we got here pi r squared. Pi is just a number, so we're just going to derive this with the power rule. The exponent will come down front, so that becomes 2 pi r to the first, and we'll give it a dr dt, the rate of change of the radius. Okay, let's go back. We want to find dA dt, and that's nice because we've got that on one side of equals all by itself. So over here is just some stuff we're going to plug and chug. 2, and we have pi. Now we need a radius, and that's when we're freezing time, when the radius is 4. And then we have the rate of change of the radius, dr dt. Well, that's equal to 1. 1. So how fast is the area changing with respect to time? dA dt is 8 pi. So when the radius is 4 feet long, the area is changing at 8 pi. Oh, and we got to come up with, there's probably some units in there, right? Rate of change of the area. So this is going to be foot squared per second. We're talking about seconds here. So that's going to be foot squared per second. So the pebble goes plop in the middle and the rings start going out 1 foot per second. At exactly the 4th second, we're out here at 4 feet. How fast is the area, the total area of the disturbed water changing? 8 pi feet squared per second. So here's some guidelines. Identify all the given quantities and quantities to be determined. Make a sketch. Label those quantities. 2, write an equation that involves the variables whose rates of change are either given or to be determined. 3, use the good old chain rule. Implicitly derive both sides with respect to time. After you have derived, then you sub into the resulting equation all known values for the variables and the rates of change. Then solve for the required rate of change. So make sure in step 4, we got to do the deriving before we plug stuff in. One thing we can plug in right away, I'll call it, the things that are set in stone. Some length or some part of the problem that is not changing at all. Those can be plugged in at any time, but the stuff that's in a constant state of change needs to stay out until after the deriving is done. So we got a table below here. It lists examples of math models involving rates of change. For instance, the rate of change in the first example is the velocity of a car. So usually the hardest part of these problems is coming up with the equation based on the mathematical model, the verbal model. And in my opinion, the first one here is the trickiest. Velocity of a car that is traveling for 1 hour is 50 miles per hour. So what's the main part of this problem? We got velocity in miles. Well, we're talking distance. X is equal to the distance car has traveled. Distance car traveled. And then it says we have the velocity of the car. Well, remember, velocity is the first derivative of position. So that would be a dx dt. How has our distance changed as time goes by? So the velocity is 50 miles per hour. 50 mph. And we could put in there when time is equal to 1 because we've traveled 1 hour. So we're going at 50 miles per hour when time, t is equal to 1. Number 2, water's being pumped into a swimming pool at a rate of 10 cubic meters per hour. So here we're talking cubic, so some kind of a volume. And where water's being pumped into a pool, so it looks like V would be the volume of H2O in the pool. Volume of H2O. How much water's in the pool? And then we've got it's being pumped in at a rate of 10 meters per second. Well, that sounds like how the volume is changing. If we're pumping water in, the volume is changing. dV, the change in the volume, dt with respect to time. And that's equal to 10 meters cubed per hour. Third one, a gear is revolving at a rate of 25 RPMs. One revolution is 2 pi radians. Remember, one trip around the unit circle is 2 pi. So what we're working on here is an angle. So theta is our angle of revolution. Angle of revolution. And then we have how it is changing. How is the angle changing? That would be the derivative of theta with respect to time. And now here it's doing 25 RPM, so that's going to be a 25. And then each of those rotations is 2 pi radians. Remember, we're talking about how an angle is changing. So we need its rotations and the value of each of those rotations. And if we multiply there, we're going to get 50 pi rads per minute. Rad per min. Last one, we got a population of bacteria that is increasing at some rate, 2,000 per hour. So here we've got a population, it's increasing. So X is our total population. Total population. How is the population changing? Well, we would derive that population, dx, with respect to time, and that's equal to 2,000 bacteria per hour. That's supposed to be an R per hour. So there we go. Just some examples of how you're going to come up with these equations and rates based on a verbal description. Sometimes it can be pretty tricky. Okay, here in example 3, we are inflating a balloon. And it says air is being pumped into a spherical balloon. Let me get my highlighter out here. Air is being pumped into a spherical balloon at a rate, there's word rate, so this is one of our rates, of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 1 foot. So this just really sticks out at me. Find rate of the radius. So when we do our given, our find, and the equation that ties it all together, looks like the given stuff just jumped right out here. Or no, a find the rate of change of the radius. So that's dr, the rate of change of the radius with respect to time. Dr dt is some value when r is equal to 1. We are going to freeze time when the radius is 1 foot and see what else is going on in the problem. Okay, air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Cubic feet, and it is spherical. So it looks like we're dealing with a volume here. The change in the volume, dV dt, as time goes by. The volume is changing at 4.5 cubic feet per minute. I like fractions a little better, so instead of 4.5, we're going to use 9/2. And the equation that ties all this together, well, they're talking about a spherical balloon. The volume of a sphere is 4/3 pi r cubed. R cubed. Ooh, now I remember from a few years ago, for some reason, I changed the radius to 2. We're not going to pause the problem when the book or when it says equal to 1 foot. Let's do it when the radius is equal to 2. Okay, I don't want to erase any of this. I'll hop to a new slide here. Volume equals 4/3 pi r cubed. We're going to derive with respect to time. So the change in volume, dV, with respect to time, dt, is equal to 4/3 and pi are just numbers, and we got an r cubed, so this is just going to be a power rule. 4/3 times 3, well, it's going to be 12/3, or 4 pi r to the second power, and then we get a dr dt from the deriving implicitly. Okay, I think we are ready to plug in the values. dV dt, that is 9/2, is equal to 4 pi times our radius squared. Well, radius is 2. We're going to square that and get a 4. And then we've got dr dt. And that's what we want to get by itself. So let's see here. We're going to have 16 pi. 9/2 equals 16 pi dr dt. So we're going to divide both sides by 16 pi. This might be weird. There's already a fraction over there, but we're going to have 9/2, and then we're going to divide that by 16 pi over 1. So that's just going to come up and flip. It's going to be 1 over 16 pi. Make note that pi is distinctly in the denominator. If we multiply straight across, we're going to have 9 over 32 pi. 9 over 32 pi. 9 over 32 pi is equal to dr dt. Now remember, this is the rate of change of the radius. How fast is the radius changing when the radius is presently 2 feet? So this number doesn't mean much to me with the pi in it. But if we do a decimal approximation, you get about 0.09 feet per minute. So let's go back to the picture. We're pumping air in the balloon. The radius of that is now exactly 2, and we're pumping it at a constant rate, and the radius is changing at 0.09, almost 1/10 of a foot per minute. And I think that's it for this problem. What's this down here? If you're taking the AP test, a decimal answer must be correct to 3 places unless it's otherwise noted. And remember, if you round a little bit in the middle of the problem and a little more later and then a little more at the end, that rounding adds up. Try to round only at the very, very end of the problem. And what the heck is this? In the example, note that the volume is increasing at a constant rate, 4.5 cubic feet per minute, but the radius is increasing at a variable rate. Just because two rates are related does not mean they are proportional. In this case, the radius is growing more and more slowly as t increases. Do you see why? Remember, we're adding 4.5 cubic feet of volume. If we have a very small balloon and we have 4.5 cubic feet of volume to put around it, it's going to seem like quite a bit to what's already there. But as the balloon increases, the layer created by another 4.5 cubic feet gets thinner and thinner. That same 4.5 cubic feet spread around a bigger balloon is going to be much thinner. So as that radius is growing, it's also slowing down. The volume increase is constant, but the radius is changing. It's a good thing they're related by time, so we can still figure out what's going on using a little simple calculus. Okay, this is a good example. 4, we're tracking the speed of an airplane with the radar station. We've got an airplane flying on it. Let me just bring this down here so I can draw in the picture as we go. Or actually, I'm going to draw my own picture to get rid of all the confusing stuff here. So the airplane is in this corner. and it's flying toward the radar station. And then the radar, ooh, that's bad. The radar station is right down here below at this vertex of the triangle. And if I remember, I think we're going to call this side S. So it's flying at a path taking it directly over the radar tracking station. The distance S is decreasing at a rate of 400 miles per hour when S equals 10. What is the speed of the plane? And let's see here. I think there's some stuff in the picture we need. An airplane is flying at an altitude of 6 miles. So the plane is 6 miles in the air, and that is not changing. So that is this side of the triangle. And then we've got this unknown side up here. And we don't need anything about the angles. And I don't think I need the picture anymore. Okay. Let's see. Given, find, and equation. Given, find, and the equation that ties it all together. Well, let's go back up to the problem. An airplane is flying on a path directly over the radar tracking station. The distance S is decreasing at 400 miles per hour when S is 10. So the distance S, this hypotenuse of the triangle, is decreasing. And they gave us that rate, so that's our given, ds dt. The side S is changing with respect to time, and that's equal, it says it's decreasing at 400 miles per hour, so we know it's 400, but it's also got to be negative because it's decreasing. And it says this is going on when S equals 10. S equals 10. And I guess, well, let's just call this side X, the missing side of the triangle. What do they want us to find? It says, what is the speed of the plane? Well, remember the plane is here, flying to the left. There's a terrible little airplane. But it's flying this way, and we want to find the speed of that plane. So that's going to be how fast x is changing. We want to find dx dt. dx dt is equal to question mark. This would be at the same time when s equals 10. So what's the equation that ties all this together? Well, if you look at my picture, this is a right triangle. It looks like it's going to be the Pythagorean theorem. Now, here, this side 6 is not changing. This side S is changing as the plane gets closer. X is obviously changing as the plane gets closer, but the altitude is constant at 6. So we can plug this 6 in right away. Our Pythagorean theorem is going to be x squared plus 6 squared, now let's just write that as 36, is equal to s squared. Okay, I'm going to start a new slide here. X squared plus 36 is equal to x squared. We are going, s squared. Let us derive implicitly. So first part here, 2x, we got a dx dt appears. 36 derives away, and then we have a 2s ds dt. Now let's see, I think they wanted dx dt. Yeah, we're solving for dx dt, so let's get this dx dt all alone. dx dt is going to equal, we're going to divide both sides by 2x, so the 2's are going to cancel. So we're going to have s over x ds, oops, that's a terrible s, ds dt. Okay, let's see what we can plug in there now. ds dt, this is negative 400. And then we've got an s divided by x. Well, they told us we're going to freeze time when s is 10. So this s in the numerator goes in at a 10. And this is equal to what we're looking for, dx dt. We need x, though. We don't have an x to put under the 10. Where is x going to come from? Well, it's going to come from where we freeze time. Here's our equation, and it's in there with all the variables. Now we're freezing time when s is 10. So let's turn this s squared into a 10 squared, or 100, is equal to 36 plus x squared. Okay, let's solve for x. Subtract 36. X squared is 64. Take the square root, you get plus or minus 8. But remember, we're dealing with the side length of a triangle, so the negative answer makes no sense. This missing side up here is 8 when we freeze time. Remember, we're freezing time to analyze this problem, and since we've frozen time, we can figure that missing side of the triangle. X is 8. 10/8 divided by negative 400. Punch that into calculator. You get negative 500 miles per hour. Now, if this is the multiple choice on the AP, this might be one of the decoy answers that they would mark wrong because they did ask us in the problem for the speed of the plane. Speed is the absolute value of velocity. If we absolute value velocity, that's equal to speed. Remember, velocity has a direction. This negative means leftward or downward direction. So to actually turn this into speed, we're going to absolute value it and get 500 miles per hour. That's how fast the plane is going. And I think that's it for this one. We got a remark down here. The velocity in this example is negative because x represents distance that is decreasing. In general, quantities that are decreasing in magnitude are represented by a negative rate. Example 5, we've got a shuttle launch and we want to track that launching shuttle with a camera. So the angle is going to be changing of the camera. Let's see what they say. Find the rate of change in the angle. Ooh, that's going to be an easy one. Find rate of change of the angle of the camera shown in the figure 10 seconds after liftoff. Given, find, equation. Find rate of change of the angle. So we want to find how the angle is changing. That's going to be a d theta dt. And our when, 10 seconds after liftoff, when t equals 10. Now here, the given part, the setup to the problem I read up here, but let's go look underneath the picture. It says a television camera at ground level is filming liftoff of a rocket rising vertically according to this position equation. S equals 50t squared. Where S is measured in feet, T is measured in seconds, the camera is 2,000 feet from the launch pad. So shortly here, I guess I can just squeeze it in here into the picture. This side of the triangle is 2,000 feet from the camera to the rocket. So we got 2,000 there. Our angle theta is here inside. And actually, let me hop to here. Draw a little better picture. Well, not a better picture. But here's theta. This side of the triangle is 2,000 feet, and our rocket is heading up. And what was that? S equals 50t squared. S equals 50t squared. And S is our height off the ground. At time 0, 0 squared times 50 is 0. Our height S is 0 feet off the ground. Plug in 1 second, square it, multiply by 50, we're 50 feet off the ground. So here is the position equation for the rocket. Is that going to be our equation here? No, because we're dealing with a triangle in the picture, a right triangle. So actually, the S equals 50t squared is our given. 50t squared. Okay. The equation that we're dealing with, remember the equation, it needs to have a theta in it. So this is not going to be Pythagorean theorem. It's not going to be S equals 50t squared. We're concerned with the rate of change of an angle. So let's look at this. We got our angle here. Opposite side is S. Adjacent side is 2,000. What trig function deals with opposites and adjacents? Well, that's tan. The tan of theta equals S over 2,000. Tan of theta equals S over 2,000. Okay, we've got our equation, given and find stuff. Let me make a new slide. Tan theta equals, and instead of S over 2,000, I'm going to write 1 2000ths s. That's the same thing. I just think it looks a little better. We slide the s off the top of the fraction, and it might make it easier to see the derivative we're about to do here. So let's derive. The derivative of tangent is secant squared of theta, and we will have a d theta dt appear. And the derivative over here, 1/2000 s, will be 1/2000 ds dt. Okay, let's get the d theta dt by itself. D theta dt equals, well, we could divide both sides by secant squared. So over here, it would all be over secant squared. Or remember, secant is 1 over cos. So an alternate way to look at this, if we multiply the left side here by 1 over cos squared, they're going to cancel. And then we would just multiply this side by 1 over, or no, we're not multiplying by 1 over cos squared, we're multiplying by cos squared. Cos squared. Because here the cos squared will turn into 1 over secant squared, that will cancel with the secant squared that's already there. So if we multiply the left side by cos squared, we're going to multiply this side also by cos squared of theta. And that's still going to be multiplied by the 1/2000ths, as well as the ds dt. Okay, let's see what we can plug in there. Whoa. The d theta dt, we do have isolated. So that's going to stay over here on the left, d theta dt. Now, where's this other stuff going to come from? We would need a cos squared of theta. Or if we could find another way to write that, would be the cos of theta and square that. Well, how in the heck are we going to find cos of theta? Well, let's go back to our triangle. Let me go to this one. The cos of theta. Remember, we set this triangle up. It was based on tan. But we can find the cos from that angle's perspective. Cos of theta, cosine is adjacent over hypotenuse. The adjacent side we have, that's 2000. But where are we going to get the hypotenuse? Well, we're going to have to solve the rest of this triangle. So let's go back here. Our freeze frame, the time we're going to stop is 10 seconds after liftoff. We need to find the height here of the rocket S. Well, look right here, S equals 50t squared. If we're freezing time, we can now find the height of the rocket, or this side length S, by plugging in a 10 for t. So t goes in, or 10 goes in for t, we square it and get 100. 100 times 50 is 5,000. So this side, S, is equal to 5,000 feet. So to figure out, this missing hypotenuse that we need here underneath our 2,000 for our cos ratio, well, let's write it like this for now. We're going to have the square root of the leg squared. Under here we're going to have a 2,000 squared. That would be our a squared. Oops. Plus our b squared. That would be 5,000. Also squared. If we square them and add them up and take the square root, that is this missing hypotenuse. And we can just leave that for now. We've still got, oops, where did that go? Oops, yeah, here we go, cos squared. I should have been writing that in there. So this cos of theta, 2,000 divided by that radical, is going to go in for this cos squared theta. Well, let me say that again. What we found here, this is cos of theta. Remember, what we want to put in here is cos squared of theta. So this cos value, 2,000 in the numerator, and then in our denominator we have a radical with 5,000 plus 2,000, or 5,000 squared, plus 2,000 squared. That's supposed to be an exponent squared. That's better. And this whole quantity is squared because, remember, this cos is squared. And now we can continue on here. We still have this 1/2000ths, 1 over 2,000. And then ds dt. I don't remember them giving that to us, ds dt. If we go back and look in the problem, no ds dt was given. They never mentioned it. But look at here. We've got s, and it's related to t. So let's derive, let me switch to blue ink, this with respect to t. Remember, we want ds dt. So if we derive that s, we're going to get a ds with respect to time. And then this makes it nice. We derive with respect to the same variable. So that derivative is just 100 t. So ds dt is 100 t. And remember, we're stopping when time is 10. So that's going to be 100 times 10, or 1,000. So this ds dt is equal to 1,000. Okay, let's see what we can do with this now. One thing, let's look here in these brackets. We've got this square root that I'm highlighting in black, and we have a quantity squared, so those are going to cancel each other out. The radical is going to disappear, so that's just going to be 5,000 squared plus 2,000 squared. Look what's here in the numerator. That's going to be 2,000 squared. There was no radical there to absorb the squaring, so this one still needs squared. And then here, if we put the 1,000 on top, 1,000 over 2,000, that's just going to be 1/2. And if we punch this in on our calculator and reduce the fraction, we'll get 2/29. And remember, our units here would be rads per second. Remember, we're talking about the changing angle as our camera tilts to track the space shuttle, and that angle is changing at some measure of radians, 2/29 radians per second. Ooh, that was a good one. I'm kind of tired. But we got one more to go, and this, I just call it the piston problem. This is the juiciest one in the section. It's the grand finale for this. This is a very good applied problem. Maybe somebody will go on and get an engineering job with one of the big car manufacturers, and you might actually be looking at something like this. In the engine shown here below, we have a 7-inch connecting rod fastened to the crank of a radius 3 inches. So here is our crankshaft, here is a connecting rod, and it's connected, that shaft is 3 inches. Or the radius of this crankshaft here is 3 inches. The crankshaft rotates counterclockwise, constant rate of 200 RPM. Find the velocity of the piston when the angle theta is exactly 1/3 pi. So here, they've sort of drawn just a triangle to see what's going on here. This crankshaft I'm highlighting in black is this side here. That's our 3-inch radius. So this is spinning in a circle counterclockwise. As that spins around, this side that is length 7 spins around, and here's connected to the end of the piston. That pushes the piston forward and back in the cylinder. This side X here is changing. Notice also in this side length 3 is not changing. It's only going to be 3 inches long, but it's rotating. This side 7, the connecting rod, is also 7 here. It's not going to change at all. The things changing in this triangle are the angle as it spins around counterclockwise, and this side length X is going to change as the piston is forced forward and backward. Okay, let me move, what the heck, oops, we don't need that just yet. Let's see here, given, find an equation. Given, find, and I'll put my equation over here. Let's see, what did they give us? Crankshaft rotates counterclockwise at a constant rate, 200 RPM. So what did they give us? Well, that's how that angle is changing. That would be our d theta dt. D theta dt, the angle is changing as it rotates around. Well, it goes around 200 RPMs, and each rotation is 2 pi rads. So let's just write this as 400 pi. Our angle is changing at 400 pi. That would be rads per minute. Or was it seconds? Now it's per minute. What they want us to find, the velocity of the piston. Remember, velocity or speed, that's the derivative of position. And here our length x is what's going to be moving back and forth. That's driving the piston forward and backward. So what we want to find is dx dt. How is that side length changing? What is its velocity? Find dx dt, set that equal to question mark, when theta equals pi over 3. Pi over 3. Okay, what is the equation that is going to tie all this together? Well, the triangle's changing. It's not a right triangle. It is for microseconds, but the triangle is not a right triangle. We're going to need the law of cosines. So for this one, the way we have it set up, here's angle theta. This side C relates to our side X. And then we have A will match up with side 3. And this 7-inch, the drive shaft, will match up with side B. So we're going to use this law of cosines equations. B squared equals A squared plus C squared minus 2AC cos of theta. So I'm just going to slide this up here a little bit, and I'll come up with my equation. Let me switch to red ink. Equation. So here we've got b squared, and for us that'll be the 7. So 7 squared equals, remember we can plug in numbers now that are set in stone and unchanging. This 7 is not changing, it's that length, that does not change at all. That's equal to a squared. A is also a side that is set in stone. This side length 3 is not going to change. So our a squared is 3 squared. That's supposed to be a squared. Plus c squared. Well, for c here, that's just this side x, and that is changing, so that's going to just stay an x, and we're going to square it. So we got the c squared part there. Now minus 2ac cos theta. Well, that'll be 2 times 3, so that'll become a 6. Our c value is x, so that's a 6x, and then a cos, that's supposed to be an s, cos theta. So there's our equation that relates all our variables. The d theta dt, the dx dt, it's all in there. And we've got our moment that we are going to freeze time. So let me start a new fresh slide so I can write this equation again, and we can derive it. 7 squared equals 3 squared plus x squared minus 6x cos of theta. Okay, let's derive. 7 squared is 49. It's a constant, derives to nothing. 3 squared, 9, constant, derives to nothing. Now here, x squared, that's going to become a 2x dx dt. Minus. Now the way I'm going to do this, let me put a set of brackets around this. We've got the 6 and then we've got an x cos theta. I'm going to keep the 6 out, and so I'm going to have some brackets here. We'll do the product rule inside, and then we'll distribute the negative 6 at the end. For me, that's the safest way to do these types of problems. I'm less prone to mistakes if we do it this way. And remember, we are deriving with respect to t. So let's see here. I'm going to do it like this. We have our first function x, and we're going to multiply that by the derivative of cos theta. Derivative of cos theta is negative sine theta, and don't forget a d theta dt. D theta dt. Plus, I'm running out of room here. Let me do this. I can shrink this up a little and maybe just get that 0 just so we remember that it's there. So there's our first times the derivative of the second plus the second, cos theta, times the derivative of the first. The derivative of x would be 1, but don't forget the dx dt. Okay, let's distribute that negative 6 now. 0 equals 2x dx dt. Here we've got a negative 6, and don't forget this negative here. That'll distribute, turn into a plus 6x sine theta d theta dt. Distribute the negative 6. This is now a negative 6 cos theta dx dt. And we are trying to get dx dt by itself. Let's see here. Should we move those to the other side? I'm just going to underline here in red. Dx dt is on this one. Here's a dx dt. Okay, this one's negative, so let's move them over to the other side where it's going to be positive. And in the same step, I'm going to factor out the dx dt so I don't have to copy all this again. So this term here is going to hop over, turn positive, and the dx dt is factored out. That's just going to leave a 6 cos theta. Here we have a 2x dx dt. That's going to come over, become a negative 2x, and we factor out the dx dt. So that means here on the other side of equals, the only thing left is 6x sine theta d theta dt. And of course, we are going to divide through by the quantity in the brackets. Dx dt is equal to 6x sine of theta d theta dt. All of that is divided by 6 cos theta minus 2x. The deriving is done. We got to start thinking about what we're going to plug so we can chug to the answer. Dx dt is what we're hunting for. And let's see, up here we've got a 6 times an x, and sine theta. They told us that theta, we're going to freeze time at 1/3 pi. So this is going to be sine of 1/3 pi. Oop, that's supposed to be a 3. And I think they gave us the d theta dt. D theta dt, that's 400 pi. So this d theta dt is going to be 400 pi. Down in the denominator, we're going to have a 6 times a cos of angle theta. That angle is 1/3 pi. And then we've got minus 2 times x. Now I put in those empty parentheses because what the heck is x? We don't have it yet. So how are we going to find x? Remember now, we've already frozen time. So if we go back to this law of cosines here, let me erase some stuff up top so I got some room to work. We've frozen time. And, we've already derived this to use, but we can now come back and use it to figure out the missing x at the moment we froze time. So before we derived this, we could write 7 squared is 49. That's going to equal 3 squared is 9 plus x squared. That's what we're looking for right there. We want to solve for that x. And then we've got a minus 6x. And then multiplying by that, we're going to have a cos. We've frozen time at 1/3 pi. That is supposed to be a 3. And I can get rid of this. Oops. Now this cos at 1/3 pi, remember on the good old unit circle, that's equal to 1/2. So this is going to turn into a 1/2 and hit this minus 6x and cut it in half to a minus 3x. And I guess let's also at the same time here, let's subtract 49 from each side. So if we subtract 49, 9 minus 49 is negative 40. Now our equation is equal to 0. X squared minus 3x minus 40 equals 0. Looks like we're going to have to factor. X squared comes from x times x. What multiplies to 40 adds up to negative 3. Well, that looks like a negative 8 and a plus 5. Yeah, negative 3 when you add them, negative 40 when you multiply. If you set each factor to 0, you get x is 8 and x is negative 5. Now remember, x here represents the side length of a triangle. Triangles cannot have negative side lengths, so there is our nonsense answer. We've now figured out when we freeze time when theta is 1/3 pi, at that exact same moment, x is equal to 8. So back here, this x is equal to 8. And it's all downhill from here. See now here, we've got a cos at pi over 3, sine at pi over 3. When we're at the 1/3 pi radian on the unit circle, our cosine value is 1/2. Our sine value is √3 over 2. So let's get this answer. Dx dt 6 times 8, well, that's 48. The sign there at a third pi, that's root 3 over 2. And we're going to multiply that by 400 pi. Down in the denominator, we've got a 6. Cos at a third pi is a half. And then we're going to minus 16. And what this turns into, the numerator, 9,600 pi times root 3, all divided by negative 13. There's our exact answer. It has two irrational components. The pi and the root 3 are irrational. But we can find this as a decimal. It might make more sense. Remember, this is our dx dt. If you punch it in the calculator and get a decimal, it's approximately negative 4,018. And what would our units be? Remember, this is the side length of that in the piston. Everything we were dealing with was in inches, and we were talking minutes. So inches per min. Inches per min. Now, what does the negative mean in the context of the problem? Remember, if we're talking velocity, negative movement is either down or to the left. So again, imagine, the piston is attached to this part of that crankshaft. This is rotating around counterclockwise. So when this angle is 1/3 as it's oriented in the picture, that means the piston is moving back to the left. We could do other snapshots, like maybe down here, where the piston would be pushed back out, and our final answer would be a positive number. But this negative means the piston at that moment is moving to the left. If we take the absolute value of that, that would be our speed. The velocity, it tells us which way we're headed also. And I think that is the end of that example. I think that's the end of the video. Here is a look at the homework. If you didn't see it in class, page 194 in the book. There's a couple problems from the book. I do have some handouts we'll do in class, and they're not worksheets. That sounds too much like work. They're fun. They're fun sheets in class. And there's a few problems on WebAssign to check out also. All right, I will see you in the next video.